Hello everyone, as you know I am Paul, your EHobby guy, and in today's video we are going to be looking at this microchip. It is a 7447 BCD to 7-segment display decoder. We're going to look at it in depth. We're going to build a circuit and go through all of the digits. What this chip does, it takes a 4-bit binary input and converts it to a decimal number between 0 and 9. We're going to take a very close look at all of the pins on this IC, look at the inputs and the outputs and how we can build a circuit so that we can display each digit from 0 to 9 onto a 7-segment display such as this. And what do these things mean anyway? We'll review this chip in its entirety, so let's jump right in. Taking a quick review at the chip here, we'll break it down really quickly. On pin 16 here we have VCC, which we're using 5 volts. Pin 8 is ground. So they're the two things that are pretty much a constant with all of these ICs. Now right here on the left side of the chip here, we have A, B, C, and D. These are the 4-bit binary input, and we're going to talk about that in a second. We'll talk about these 3 pins, 3, 4, and 5, closer to the end of the video. We have the outputs all on one side, which is nice and convenient, especially for breadboarding. We have the outputs A, B, C, D, E, F, and G, of course. 7-segment displays are very clearly labeled from A to G in this configuration. And so the output here, A, is going to go into the pin on the 7-segment display for the A, this top LED, and so on. B would go in here, C, D, E, F, and then G in the middle. So in quick review again, the 4 inputs here are capital letters A, B, C, and D. We're going to talk about these 3 pins, which have a bar over here, and that means active low. These 3 we'll talk about in a while. VCC on pin 1, ground pin 8, and the 7 outputs driving the 7 LEDs in a 7-segment display. Before we go to the breadboard though, I do want to talk about why we have 4 inputs. Now these inputs are binary inputs, meaning that it's either going to be high or low, a 1 or a 0, 5 volts or 0 volts. Each of these pins have 2 possible states that it can be in. So let's just take a look at why we need 4 and why not 5 or 3 or 2. When we're using the decimal system, we count starting at 0 and we count up to 9. So if we're counting, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we want to go one more, we add 1 to the 9. We bring the digit back to 0 and we come to a preceding number and we add 1 to that. If there's nothing there, we assume a 0. We pretend we counted to 9, we added 1 more, bringing us to 10. We bring this to the lowest number, which is 0, and we just add 1 to the preceding digit. And adding 1 to the preceding digit would give us 10. Then we would keep counting here, and when we get back up to 9, meaning 19, we would go 1 more, bringing this to 2. So you add 1 to the preceding digit and bring this back to its lowest number. That would bring it to 20. In a binary system, each digit can only exist in 2 states. And so when you're counting in binary, the lowest number is 0, and then we count up to 1. They're the 2 possible states that it can exist in. Now remember what I said, when you get up to the maximum digit, if you want to add 1 more, we bring the 1 down to its lowest again, and we add 1 to the preceding. And if there's nothing there, you make it a 0. Adding 1 to 0 gives 1. And so in binary, 0, 1, this would be a 2. So if you had a 1 and a 0 in a binary counting system, this would be 2. We could add another digit. We keep adding to the least significant digit. And so we add 1. So in binary, this 1, 1 would be equal to a 3 in decimal. So let's keep going. Let's add another 1 to this. So adding 1 to this, we've reached its maximum, so we bring it to its minimum, its lowest number, and we add 1 to the previous digit. Now this is also already at 1 at its highest, so we bring that down to 0. And we add 1 to the preceding digit to that. And so when counting, this would be 4. Let's continue adding 1 here, using the same logic. 1, 0, 1. Adding 1 more to this. Again, we're going to cascade the zeros. That goes to 0, like we said, but we add 1 to the previous digit. That's already at its max, so we go a 0 here. Adding 1 to the previous digit, that's at its max, so we'll put a 0 here, and add 1 to a previous digit. If there is none, put 1. So an 8 in binary is represented by 1000. It's not 1,000. 1,000 is the decimal 1000. In binary, 1000 is actually just an 8. With only 3 digits, we get 0 to 7. We can't get any higher. We must add a 4th binary digit to get above the number 7. And so once we get to that 4th digit, that can continue all the way up to 16 in binary, actually in hexadecimal. I'll just continue it going up to the 9. The 10 is of no interest to me right now, because we're only looking at 1 digit, and it's going to count from 0 to 9. That's 10 digits, 0 to 9. So just to restate, if we only had 3 binary inputs, we would only get up from 0 to 7. We'd only get 8 digits. I want a total of 10, and so that's why we add the 4 digits. Looking back here, just to recap, that's why we have 1, 2, 3, 4 input digits that are binary. With this understood, we'll jump over to the breadboard. I put something together. I didn't want to bore you with the build for that. It is very clearly laid out, and then I'll talk about what we did, and we'll take it from there. And so I'm holding this chip oriented like this because that's how I laid it out on my breadboard. So we're going to look at the breadboard right here. So if you look at this chip, the notch is at this end, notch is at this end. I'll zoom in just a little bit. Looking at the A, that's going to be all the way on my right. That's this button right here. B is going to go all the way over here. And so I have jumpers going to the chip right here. A is going to the second last pin on this side. That's the black wire. The B is going to the pin that's all the way up here. That's the green wire. Is coming up to pin number 1 on the chip here. So I want them to be in order as I'm doing the inputs. I want to be able to follow this and be able to easily count from 0 to 9. So I'm making them A, B, C, and D. I just wanted to make clear here what I'm doing with the buttons and how they're hooked up. I'm jumping 5 volts to each of the buttons. So on one side we have 5 volts on this button. Each button on this side has a pull down resistor. I'm using 470 ohm resistors as pull down resistors. Each one of these are going to the negative rail right here. Here's the blue for negative, red for positive. I'm going positive to one side of this opened momentary switch, and I'm pulling it down to ground with a 470 ohm resistor on this side. Now we're taking this low side and jumping from here to each of the A, B, C, D inputs. Just wanted to make that clear. Now getting a closer look at the 7447 chip, I just want to show you the 3 pins that represent these 3. 1, 2, 3. These 3 for now are just going to be tied together and pulled high. Right here there's a small jumper, and right here there's a small jumper. So all 3 of these pins are tied together, and right here I have a jumper going from any one of these 3. I'm pulling them high right here. Now jumping to the other 2 things, which are the simplest of all. VCC is to pin number 16 right here. Pin 8 is being pulled to ground here. Now looking at the outputs. For clarity, I just wanted everything to be nice and parallel, because the pins, as we looked at a little earlier, start at this pin right here, which you can't really see, but it's the 4th pin down, 16, 15, 14, 13. It goes A, B, C, D, E, and then comes to the 15 pin F, and then G. They would be jumping over each other, and it may make it a little confusing. And so what I did, just for clarity, is I brought these current limiting resistors up to the board here so that it could light the LEDs right here. And so looking at the output here, we have one LED that's out. Now I'm not pressing any buttons at all. And what that means is that a 0 should be displayed on a 7-segment display like this. And if you look at it on a 7-segment display, all should be lit except the center LED, which is a G. This is the G, and so it is looking promising right now. All are lit. If I press the 1, starting here, A, B, C, B and C should be the only ones that are lit. So let me press a 1 right now. I'll zoom out a little bit. I'm just going to press 1, and there we go. B and C, 2 LEDs are lit. So what we're going to do is just replace these with a 7-segment display. I did have a problem though, and I'll explain briefly what my problem was when trying to set this system up. Here I had a sleeve of the 7447 chips. Now I was using these chips to set this up. I have it nicely labeled here. Things weren't right. I was getting very erratic outputs. And so I kept trying and trying and trying, and each chip would give me different outputs. And I'll just give you an example quickly right now. I'm going to power this down, and remember this pattern, we're just going to have one LED out. I'm going to pop one of these in. I just want to show you what I found when I was building this. Okay, I popped this bad chip out for that good chip, and I'm going to give it some power now. And remember, we would have had a 0 with one LED out right here. I'm going to give this power. See what I get? Complete junk. And even when I give different inputs, nothing happens. This was very frustrating. I actually went through this entire sleeve, and I realized I actually was giving up on it, thinking that something was wrong. All of these chips were bad. I'm going to switch to good chip back, and we'll talk very briefly about the other problem I had and what I did to fix it. Now the second problem I had is that the 7447 IC is to be used with a 7-segment display that has a common anode. Now I have a lot of 7-segment displays here, and some scavenged and some brand new here. Out of all of them, I didn't have any common anode. It's a freak of nature as far as I'm concerned. I didn't have any common anode 7-segment displays. I only have common cathode. I've since ordered some, but I figured I would take it as an opportunity to just, hey, let's make my own. I mean, we have a lot of LEDs, and that's all they are. They're just LEDs. So I took the opportunity to make this, and this is my own 7-segment display. Now I'm using 2 LEDs just for clarity. It's a little easier to read when you have 2 LEDs. These top 2 LEDs right here would be my A segment, B segment, C segment, D, E, F, and these 2 middle, G. And what I did to make it a common anode is I just joined all of the anodes together and put them on this right-hand rail right here. So all of these with the jumpers underneath there are all joined into the anode right down here, and we'll give it power when the time comes. So I built my own 7-segment display. We'll use it as a test display to go through the function of the chip. Now in addition to joining all of the anodes to each other, I did have to join the cathodes of each segment. So these 2 LEDs have their cathodes joined, these 2 LEDs have their cathodes joined, and so on all the way around. And this way, when I get a signal in, it's going to trigger both LEDs for that particular segment. So right now we're at a juncture where I have these in the order in which they're just pinned out here, just for clarity to show you that they do light up. It's clear to follow them through. So what I'm going to do is take these away and jumper each one of these. It starts, I believe, here, A, B, C, D, E, then F and G. Going to jump them over to the segments on my own 7 segments display right here. I'll give it some power, and we should get a 0, and yes, we got a 0. Pressing this button right here should give me a 1. So segments A, B, C, B and C should be lit for 1. Let's check that. There's a 1. Now coming here for a 2, there's 2. A 1, 1 is 3. There we go. It's a nice 3. Pressing the third button here by itself is a 4. There's a 4. Adding this digit here is a 5. And then getting to this is a 6. Adding a third, these 3 is 7. All relieved to 0, but 8 is this 1 press. There it is. All 7 segments are lit, and that's an 8. And then adding this least significant bit right here should give me a 9. And there's a 9. So I'll go through them quickly again. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We're getting 0 to 9. Looking at my display here, there's enough sinking current in each one of these to drive 2 LEDs. But what if you wanted to make 7-segment display in a billboard or something very large like a time clock, a sports time clock, you could easily trigger a transistor that can handle many LEDs. So just keep that in mind, that right off the chip we can drive 2 LEDs from each one of the outputs. I just pressed 8 here so they're all lit. But you could go 4, 9, 10, 20 LEDs, making a 1 foot, a 2 foot digit onto a billboard sized or a scoreboard sized display, and simply drive transistors to drive many LEDs and make your display as big as you possibly could want it to be. And from the transistors, instead of using the transistors to drive many LEDs, you could use the transistor to perhaps drive a relay. And relays can take very high currents, and perhaps you can get displays up to several feet, 10 feet high. It's really up to your imagination, your understanding of it. Think about if you have any further thoughts on that. Leave comments down below. I love hearing all about them. There are a couple of things I just want to touch on here before we wrap it up. The first thing is, even though this works and is designed to work with a common anode 7-segment display, you could use a common cathode 7-segment display like the ones that I have. To do that, we would have to just invert all of the outputs. In other words, any output that is high, we could switch it to low, and any output that is low, we switch it to high. And so we would need inverters, also known as NOT gates. And there are a few ways that we can achieve that, and in fact I did work one up, and this is using a simple transistor. So I use 7 here in parallel. I didn't want to make this video so long and go through all of this. I will leave a schematic in the description, and these are all 2N2222 NPN transistors. But you can use a transistor to, in essence, be an inverter. There are 2 other ways that I want to touch on that are very easy. Of course, you could just buy inverter ICs, and this is the 7400 IC. It's a quad 2-input NAND gate. Quad meaning 4, so there's 4 in each chip NAND gate, and I need a total of 7, and so I would use 2 of these ICs just to invert this. And I'll touch really quickly on how you use a NAND gate as an inverter. Here is the symbol for a NAND gate. It has 2 inputs and an output. To make a NAND gate like this, an inverter, simply join the 2 inputs, and any input that you give is going to be inverted on the output. So a high on the input would be a low on the output, and conversely a low on the input would give a high on the output. The third and final method is using hex inverters. So there's hex meaning 6 inverters are on these, and who knows, I'm not sure internally how they achieve that. There are 6 inverters on each one of these 7404 ICs. Because there are 6, we would have to use 2 of these because we need a total of 7, and these would achieve the exact same as the quad 2-input NAND gate ICs. And so there are 3 very simple ways that you could invert the output of this 7447, and you could use a common cathode display. And so I'm going to put that challenge out to you. Try to make this happen. I'd love to hear about it in the comments below. And now let's wrap it up by talking once again briefly about these 3 inputs. LT stands for lamp test. If we pull this low, what we're doing is we're going to set all of the outputs to be active. Now, some of the outputs with these 7-segment displays have decimal points, like this one right here. So all 7 segments of the display would be active, and the 8th decimal point would also be active if you pulled the lamp test into its low state. One thing to note about the lamp test is that this input needs to be high if the lamp test is pulled low in order for all of the outputs to become active. Now BI here stands for blanking input, and again it's active low. Now the blanking input can be used with pulse width modulation. So we can use pulse width modulation to blank this at a very high frequency, control the intensity of all of the outputs. And so that's typically how blanking input would be used. You could also just turn it off completely if you didn't want it to be seen, depending on the conditions and the application that you may be using it. So now looking at the RBO and the RBI pins on this chip. RBO, ripple blanking output, ripple blanking input. The word ripple refers to the zeros that are insignificant in front of the actual number that matters. And so let's say you have a 5-digit number that reads 00051. it's much more pleasing to just look at the two digits and have the only two digits that matter, the 5 and the 1, to be lit up. And so we'd like to get rid of the preceding 3 zeros, and we can do that with these. Those zeros are the zeros that are rippled forward. And so to achieve the blanking of the zeros that don't matter, you take the ripple blanking output from here and you put it into the ripple blanking input of the preceding chip. And you do that with all of the 5 digits that matter in the display that you're working with. If you're only working with 2 digits, you would simply take the ripple blanking output of your least significant bit and put it to the ripple blanking input of your most significant bit. That completes the explanation of these. Let me know what you think about that. Certainly, I love to hear comments down below on anything that we've talked about in this video. I hope that I've shed some light into the use of this 7447 IC. Hopefully you learned something. I'm going to leave the schematic to all of this in the description below to download. I really do appreciate you taking the time to watch this video. Follow me on social media. Check me out on my website at any time. Subscribe to this channel by clicking the circle that's right in the middle of your screen right now. Again, thank you for watching, and I'll see you next time.